Hi again. My name is Dmitry Chuyko, and we're going to talk about simple things, at least simple in making them, simply making tweaks to help your production run better. Why do we need it? Well, sometimes we do need it. I'm, uh, I'm one of developers of the platform, happy to be one. I also work in a company that releases its own binary distribution of OpenJDK called Liberca JDK and participates in various open source initiatives. And that distribution is, if you know that probably, is the default distribution in Spring Boot containers if you build Spring Boot containers using command line. You'll have Liberca JDK inside. And also we release our own distribution of Graal VM, which is called Liberca NIC, and Linux distribution, by the way. And we contribute to OpenJDK, obviously. So, getting back to the topic. We develop some software. Or some part or some other team deploys that software, right? And some team monitors the software and manages and resolves or escalates incidents with that software. And we'll kind of try to make teamwork of different teams. And there's business who pays to all the teams, right? We need to feed our developers, we need to pay them, and we need to pay different developers and different technical teams who support probably the cloud or some other infrastructure to run our application. And if we developed it somehow in a hurry, just to make it by the date, probably there's some underutilization going on. Because if we don't think about utilization, resource utilization, we have this situation. And also sometimes different things happen. Our load may increase, right? Any sale day or any other event may occur, or some failure may occur. And we start to optimize and prepare our production, our services to work in a, under high pressure. So we start to realize what high pressure is and how to deal with it. Though sometimes not. Here's a question, well, my favorite. Who knows about your neighbor team leaving Java options default for their application? Aha! And who knows such about their team? Thank you, honest man. And others who raised their hands for the first time, they are the other team for the other team. So I know that you have it. So that default Java options, that's the first and major shame discussed here today. And also, who else have seen CMS configurations that are being applied to G1? Okay, you're young developers. There are also some other things, of course. We may just spend additional resources trying to solve everything with horizontal scaling or both vertical and horizontal scaling, just spending enormous amount of money trying to solve problems that we don't have to solve because the root cause may be different, quite different. So let's take some example. I frequently use a well-known Spring Boot example called Pet Clinic to show what we can observe with this application. In this case today, like applying some tweaks. So we can containerize that application in different ways and deploy it somewhere. In my examples, for example, right here on this computer, we can deploy it and get some performance metrics out of it. Though previously I've done some experiments, got some data, but general idea here is when we have an application and we have some resources we pay for, we want to utilize what we pay for. If we pay for memory, if we pay for disk, for processor, we must use it. We must make performance out of it, right? And also, the technology that we use to deploy our applications in containers allows different sizing of resources. It allows using same hardware resources for different logical deployment schemas, right? You can have different number of pods on the same node. So you must test and prepare your deployment correctly to get the maximum or at least good performance. So this application on this machine runs pretty well, and it scales horizontally with some replicas, like not maybe even not on this machine, but it's the same situation. Like it works well with 8 CPUs and 16 gigabytes of memory per pod. And it makes it work better than having a single instance on the same machine, or more instances on the same machine than this golden amount in that series of experiments. So I will continue with that configuration, single configuration. So hey, can we make the resource usage of this application or some performance characteristics of this application, this exact replica, better? Well, obviously we have some hope that it can be made better. So first of all, before running that application, we deploy it. And even here, we may save or prepare for, I wouldn't say for worst, but at least we can make it better. Who sees any problems in this famous Docker file? From the line number 1, yes. Latest. By some chance, this is the most popular answer. Thank you to this question. Any other problems? Yes. Root access. Great. Yes. Others? Yes. Which system? Oh, file system. Okay. Snapshot. No, that's not a problem. That's just a version. So, though, if you really manage your application lifecycle, that's also a problem. Great catch. Yeah. So, the first word, OpenJDK latest. What is the container? In fact, this is a container, and if you go to this images page on Docker Hub, you'll read that it's deprecated. Please don't use it. It's not supported. Well, yet everyone still continues doing that. So even if it's latest or not, it's deprecated just at all. And it's also a very kind of bloated image. Here we also have default Java options, the scene number 1 that I mentioned. So how can we make it better? I removed that non-root user, by the way, is again good mention. So we can use the exact tag, right? We can take a slimmer distribution, and we can even take kind of so-called JRE distribution. Well, it's minimized and doesn't contain some development tools, like JavaC compiler. We can go beyond that. In the previous example, we have deployed a fat jar. And the fat jar is kind of fat. And it's not harmless to deploy a lot of replicas of fat applications. So it's better to extract layers out of that fat jar and have only your tiniest layer updated, because you write the least amount of code of the application that you deploy. And it's in the last layer. And also you can see 2 cool JVM kind of tweaks here, or dopes. First, of course, is to use a better Java options. They are not empty anymore. So what do we do here? We change the default heap size to 80, right? 80% of the memory available for us on the pod, which raises it from which value? No, not 50. 25. Otherwise, you waste 3/3 of your memory that you pay for, or your business pays for nothing. You just don't use it at all. You don't try to use it. Well, it can be used for some native memory allocations, of course, but we rarely see that, right? The dominating memory consumption spot is Java heap, typically. So we can give that memory, even if it's not for application, give it to your garbage collector. Let it work, let it breathe, and it will give you better latency, even if you don't need it for caching or whatever purposes. And the last one is we switch from using the custom class loader that loads libraries packed in jars, packed inside a jar, by using just classes and jar files on your regular class path, which is the last line. Surprisingly, that's also a trick, right? Now to run your application using the exact main class name, not your jar name. All right, so we were able to run the application, and let's put some load in it. Though in my examples, I don't try to squeeze the maximum of the application. I say, let's make the situation repeatable. Let's see how our tweaks change the behavior application under the same load. So let it be a constant load of like 1,000 requests per second. And this application runs and it gets this load after it starts. It's not a problem. So we run it on hotspot JVM, right, on OpenJDK, Liberica JDK in particular. And by default, you will use, if you don't specify any options, you will use server VM. And who knows, other VMs available, typically in JDK distributions, like Liberica Standard, besides the server VM. If it's not server, what could it be? Okay, client. And there's also minimal. And there are also other VMs that may be built but that are typically not included. So these diagrams show us a lot. Basically, three things. The left one shows two metrics. The red metric is the CPU consumption. The amount higher than 100% means like 200% is 2 cores, right? And the blue line shows us memory consumption, the process memory consumption, not Java heap consumption, but the memory that's been attributed to this process by the operating system. And on this chart, what can we see? We can see a very slim initial peak. This is the application start. So what happens with your application when it's started, before it starts accepting connections? Which happens after this canyon. So the canyon is the application has started, but it hasn't started accepting connections yet. And the harness waits for it to start, and after that it just applies the load. So when the application starts, we load a lot of classes. We compile some methods because we initialize that classes, right? We run that initialization code. We finally start our beans because it's Spring Boot, right? We perform all that work and it's Java code that's being run and it's being JIT compiled, optimized. We load classes, we occupy heap. So both CPU consumption and memory consumption grow. And after that, there's a small countdown. That's canyon. We can slow down a little bit. We don't need so much memory. If we pause the application before applying the load, we can even return some memory to the system. But anyway, so the CPU consumption drops. And after that, we start our load. And what happens to the application? You again see the growth of both CPU consumption and memory consumption. But after some time, the CPU consumption drops. And you remember, it's a fixed rate load. So it's still the same number of requests per second. So why does the application require less CPU? What happens? Yeah, JIT optimizations, they finally stop being applied. So we don't longer need to JIT compile as many methods methods as before. We don't have to execute methods in the interpreter. We have JIT compile them. So we are in an optimal situation. So it's a warmed up application. So this is the warm-up time. And those plots are a bit kind of cheaty for this setup, but they really reflect something that happens in real world. So it's not kind of fixed frequency setup for the CPU. It actually can drop on this machine. It can drop to less than 2 CPUs. But anyway, so that's what happens with CPU. And what happens with memory? You see that it grows, yeah, and it kind of stabilizes, right? So it becomes a stable situation. GC is able to manage the workload, so it collects the garbage periodically. It's the same pattern of the workload, so it's kind of stable. It looks stable. On the right, we can observe the chart that reflects the user perception of this process. So these are average response times per second for this application. So you see that it starts from very high response times, and then response times lowers. So we have that startup, which is not seen here, right, because the application doesn't accept connections. And then there's a warm-up, which in this case lasts like 41 seconds. And how do you think, how long does it take for real applications to warm up? Like, any guesses? Sometimes hours, yeah, it may be the case, not that frequent. Well, typically minutes. Minutes, maybe half an hour. That's a quite regular situation. So you have bad response times, bad quality of service until you're warmed up. And during all the time, you have that second peak of your CPU consumption. So the first peak is related to startup, right? So you spend time, you spend CPU, and then you have that second peak of JIT compilations, of performing different VM tasks. So it's kind of resource consuming. But after that, you waste the resources because you don't need as much CPU as before. And here's a question. What is the CPU limit in your Docker or Kubernetes that you have to set for such an application? How many CPUs should assign to it? 4. Why? Yes, because that's the maximum that you need. So that you can observe the maximum blindly and say, hey, it's 4. So we can't make it faster, right? So it works well, and it won't work better than that. And what happens if we set it to 2 cores? Yes, we'll have much longer warm-up. Sometimes we won't be able to even perform the startup, because the startup phase also requires a lot of CPU. And it can become just enormously long, and we'll have timeout waiting for our Spring Boot service to start. It won't show up that up JSON response, right, in its health check. Oh, our services don't start. So yeah. You could set it to 3. Maybe. We don't know. But that definitely will waste 1 core on the long run. And it will make the warm-up longer. So we have to get the picture. We have to measure what happens if we set it to 3. Otherwise, that won't just work. All right. So we saw the server VM. But in fact, we can, as I mentioned, we have several VMs. So let's replace one. 2 kind of easy options. We don't need exotic scenarios like J9, for example, even here. We can just try client VM. The client VM that can be easily used with your Java applications. You can, in fact, specify a JLink flag and say, hey, please make this application use client VM for me. And that greatly reduces startup. though it has some consequences and in higher latency and low throughput, though it's not that dramatical as your footprint gain. Or you can use native image, which has kind of been famous for that low memory consumption, etc., etc., etc. Though, you see, savings are the same. And it will also show a different throughput picture. So with the client VM. So here's the original one on the left, and on the right is the same chart, but for your different VM option. And you see that we have greatly decreased, so the scale is different on those charts. On right chart, the maximum heat consumption is like 275 megabytes. That's it. You don't need to write programs in Go anymore. Just use Java and use client VM. Please do that. And we also have greatly shortened the startup phase, right? We eliminated the first peak. You don't need it to be such rude. And it definitely influences warm-up. So you see the warm-up now happens in, 5 seconds instead of 40. Much faster. Yes, we have visibly worse throughput, big performance. But maybe that's okay. Maybe that's an acceptable level of performance. If our application still just needs to survive 1,000 requests per second, that works. All right, what happens with Graal VM and native image? Again, original graphic is on the left, and the tested configuration is on the right. And you see, we still have that kind of second peak. We don't have the first peak because it's native image. We've compiled many methods statically and those methods kind of, we've performed a lot of initialization statically ahead of time. So we, not entirely, but mostly eliminated the first peak. But we still had the second peak, right? We still have to do things the first time when the requests come. We still have to perform some initialization. But after that, the picture qualitatively looks the same, but we again spend much less memory in this application. Though, still we have worse throughput, but we have no warm-up, almost no warm-up. There is still some, but literally latency stays quite stable. Yes? Oh, it's just a pause. So the canyon is paused, so we don't put the load, we just wait certain amount of time before putting the load on the application. So you see, we've just stripped the first part. But the client VM wasn't too bad. And client VM lets us stay within same hotspot with all the debugging tools, all our familiar things, bytecode, etc., without switching entirely to native image, which is sometimes, hard. All right. As we discussed startup, I will just recap briefly. So we have other options here. Let's still continue working on that first peak and stay within original VM. Or it can be client VM, or it can be server VM, but still we stay with hotspot. So we have application class data sharing, a technology that currently evolves into something bigger, but as a core technology, it just lets you to store the loaded classes and don't spend your resources for loading it once again, decoding all this and constructing all the data structures, verifying your bytecode, and all what happens during your initialization phase. All that is just stored in a memory snapshot on your disk in your container as an option, and you just memory map it on startup. And CRaC does quite similar thing, coordinated to restore a checkpoint. But it freezes the entire process with all its data, all your Java heap, all your code cache with your JIT compiled methods. Everything is being stored on disk. Obviously, that takes that, like, how much memory was it originally? Was it 700 megabytes, right? But we kind of compress zeros, etc. So it will be still hundreds megabytes on disks. With AppCDS, it's like tens of megabytes, which is much smaller. But CRaC has one more interesting advantage. Native image performs some initialization on loading anyway. But if we snapshot the process, we don't need to perform that initialization because it's kind of effectively performed. We restore it in initialized state. So let's look at results. Again, with the server VM, and if we put AppCDS into the game, we narrow the first peak. We can't eliminate it by this technology. We can't eliminate it entirely, but we narrow it and make it slimmer. We lower the CPU consumption a little bit, but it's still there. But the picture looks very similar. So we mostly work on that first peak. And with CRaC, we just cut it entirely because we restore exactly at the canyon point. So we start from there. There's also slight memory saving related to technology, maybe not visible on this plot, but still interesting. So as we talk about memory, we can go to other memory-related tunings. And obviously, the most famous tweaks are just garbage collectors. Just determine the metric that is important for you. That is the key metric. And optimize your basic JVM options to try to achieve that, or at least to make it not bad. We can put it in just 3 groups, right? Latency, throughput, and footprint. And there are basic GC options that allow us to optimize for that goals. There are more of them, but imagine we know the key metric, like latency, for example, but we still need to determine the right amount of memory we need for our application, including garbage collection, including its business logic. So how much memory do we need? And no other way to do it but experiments. So we have to run it, we have to analyze the output, and we have to put proper options for the planned kinds of ports that we are going to use. That may be hard. We work with some high-level abstracts, like, for example, some acceptors in our application server. But we must go from that high-level abstracts to low-level abstracts just to some bytes to see how many bytes do we need from our operating system to provide to the JVM, and what do we need in terms of native memory. And also, we usually leave some headroom. So what does your monitoring say if you kind of consume 80% of memory in your container? Is it a red flag or not? Is it a red flag? Okay, if you consume 99% of your memory in container, is it a red flag? Yes. Why? Why do you need that 1%? What for? Sorry? Request bytes? Spikes. But is that 1% enough to survive spikes or not? Or do you really need that? Maybe it's 1/10%. Okay, that's a question here. Yes, spikes. That's a good answer, because that's a planning for failure, right? Planning for spikes. What are you going to do if half of your replicas just turn off? What's your plan? Do you want to raise? Do you want to create new ones, or do you want to let the ones that stay survive all the load? So how much extra capacity do you need? How do you manage the load? So what results do you expect? And that influences the headroom that you need. And it's true both for CPU and memory. So just you need to experiment and see how your entire system behaves under certain scenarios. Right. Not just blindly leaving that. We'll leave 20% and don't use them. We use them never. Just because. Otherwise it's red. Why red? Because it's 80. All right, so it's all kind of complicated. To determine all that memory settings, to put them, to write Docker files, lots of stuff. Why do we ever need Docker files? Actually, we don't. It's just easy to use built-in tools. Just say, hey, my precious framework, please create an effective container for me instead of me as developer or DevOps. Just I have my project. Make a container image. That's it. It's possible. Just it happens. You don't need to write your Docker file. You don't need to generate it. There's no Docker file. It's just your Docker image. And it already will have layered libraries. It will already have some detection of your memory settings. It will already have some optimized size for your base OS layer and your JDK. Awesome. Though it's kind of less configurable sometimes. But if it's configurable using your high-level abstracts. Like I mentioned, the number of Tomcat threads. Just provide it. And the amount of memory, that native memory you need to run those threads, that you have to reserve from your operating system as native memory, will be automatically calculated. That's it. You don't need to do it yourself. And so your final container image will contain a special starter script that will perform all the calculations and replace itself as a process with your Java process with write JVM flags. Right, what else can we expect? As I mentioned, AOT is only a start. And that's extended support for caching your JIT code, your dynamically generated kind of code. That all is going to be cached sooner or later when Project Leyden will be implemented, finally and merged into OpenJDK. So, but you can already try it. You can try the early work in Project Leyden with your application and see benefits that it can bring. Another project, which is already available in GA JDKs, Project Lilliput, aim to reduce the overhead that JVMs have for being a managed runtime. So to be a managed runtime, you can't just have a pointer. You have a lot of meta information. So if you have an object, just an object of class object, you will spend up to 128 bytes on JDK 21 to have that meta information for the empty object, which contains 0 bytes. Oh, sorry, not bytes, bits. That's a lot. And that number can be reduced thanks to Roman Kanka. And it's already available in JDK 24, so you can enable compact headers. And you will decrease your heap usage. And sometimes it's very impressive. But for many applications, it's just visible, and clearly it's a good bonus. It's a free dope. You just turn it on, that's it. And it's already switched to a production flag in JDK 25, which is being developed. So we can see great results, right? We're not changing the compiler. We don't hurt the peak performance, but we have faster. We have smaller heap consumption. We see the same application. We just turn it on, though we compared Java 21 and 24, but 24 picture on the left is about the same. And we save hundreds of megabytes of memory. And the more, so it's not just the constant space saving. it's a percentage being saved. So for every object, we save some share of the memory that we need for that object. And though of course, the requests per second performance looks about the same, though the latency is slightly better just because GC needs, in this case, GC needs to perform less work. Other upcoming dopes are virtual threads, of course. We now, not upcoming, but available dopes. We can enable virtual threads and create millions of threads in our application. Just program creating lots of threads. Just be sure that they're virtual and won't have, it won't hurt performance that much as having even, I don't know, thousands of platform threads, which will kill your application. So we can scale vertically easily now, right? We can have a lot of threads, not a problem anymore. We don't need to write asynchronous code. We have a lot of memory, just we have low latency GCs managing that for us. But we must not be stupid, right? And we don't have to wait on logs all the time instead of performing the work in parallel. But what happens with all the systems, right? We have systems up and running for decades. But sometimes spikes happen. And people come and ask, hey, you actually are responsible for a system that's been written 10 years ago. Nobody supports it, but it was running well for all those years. But now it doesn't run well. Please make it better. Oh, we'll use the new JDK. No, we won't, because our frameworks that we depend on, that we use in that application, they're not compatible with new JDKs. Sadly, sometimes we had to stick to all the JDKs, so we won't be able to use all that cool features that newer JDKs have. So what's the response here? Well, as JDK vendor, we started experimenting with bringing more performance fixes to all the JDKs. In particular, JDKs that we provide as a cloud JDKs. So it's OpenJDK, but with extra fixes from newer OpenJDK. And it's also smaller and somehow more performant. Though it turned to be not the full solution. So we still are able just to improve things a little bit. And we decided, why won't we just take the entire new JVM and bring to that old JDK? So the applications won't notice they run on the newer VM. And it turned to be possible. We just literally did that. Just let's replace the core. Let's replace the invisible level to a newer JVM and improve performance. Bring that new features, bring new garbage collectors. Bring compact string support. Just it happens under the hood. You can also tweak some new flags. Of course, not everything is portable in this way, but it's not like bringing some fixes to all the JDK. It's like really bringing the core JDK, core JVM from a newer version to older version. And that also happens to help well-known benchmarks, and it really helps truly existing legacy applications. So it's not just an experiment. This is a working solution that, for example, easily allows you to enlarge your heap. Like you had an older instance, you couldn't enlarge your machine just because you started having too long GC pauses. Though with that JDK combined with a newer JVM, you can do that. So you can utilize newer hardware without migration. In particular, that's so true for Spring Boot 2.7, which is kind of new, lowest LTS Spring Boot that we have. And it typically runs just on all the JDKs. That's the case. So we have observed improvements in different major characteristics, in different benchmarks, in throughput, latency, and even footprint, of course, and startup time, for sure. So using all the techniques, fuse JDKs, virtual threads, right? Garbage collectors. And just turn from that hamster, from that upset hamster, into that happy hamster, who just knows that yes, there are ways to improve your application without much harm. Thanks. All right. Good question. Are there t-shirts to give away? Unfortunately, no, but yeah, continue asking. Let's have questions from the audience, or you can use Slido. So we have 5 minutes still. So I'd really appreciate questions. What's the most interesting slide? What wasn't clear, or what's the most shocking? Yes. Like this, or client VM. Yes. The CPU is about the same. It stays higher when the application warms up, because we have worse quality of the code, of the JIT compiled code, right? At some point. So it depends on the order of compilation and complexity of compilation that you have for JIT compilers. So it can be both directions. Yes. It's just how. So we can imagine two questions. How exactly this data has been collected? That's here. If you want to use CRaC, how would you create a snapshot, right? All right. So imagine we are going to deploy in containers. That's probably the most important case here. So deploy a container with a correct snapshot. During your Docker build, I would suggest a two-stage process. It could be made within Docker build boundaries, but it's fragile from my perspective. So you create a container that performs a snapshot. So its entry point says perform a snapshot. And you run this container. So at first you describe, like imagine we write Docker file, right? So we say, hey, run the application with the CRaC options to perform to create a checkpoint. And you run this container, and you create a checkpoint, and it kind of continue running, right? So your application has closed, you created a checkpoint. It's in the container. And after that, you commit the container, and you change the entry point. Thus, you will have your snapshot as an additional file layer in your new container image. And you have new entry point that will use that created snapshot. Yes. Do you need to run it on the same CPU architecture? Yes. You need to run it on the same or more common. Yes, you need to run it on same or more common CPU architecture. So you must provide hardware compatibility between environments where you build your container image and when you run your container image, in case you use technologies like CRaC. And currently, that's also probably true for Leyden. Yeah, great question. Yeah. 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 Excellent question. Yeah. So is it possible to throw more CPU power for the startup phase for the container? Yes, it's possible, though Java won't know it. So we have certain limit, and Java looks at limits. So it focuses on that long tail part of its life, which is good for this scenario. And Kubernetes and modern clouds, probably you need to put some beta checkbox or whatever. They support that so-called turbo boost for your containers. Though it doesn't necessarily work, and especially it won't work if you start your entire node at once. So if you start all the pods and they kind of expected to consume all the CPU, you don't have CPU resource to give them. But yes, if you start it from time to time and you have spare CPU resource, obviously that's a good option to use. So it's possible Kubernetes is able to do that, and clouds are able to provide you such an option as a UI or CLI option. Are we done? All right, thanks again.